confirming the performance of a reusable rocket engine, including several other aspects of it, such as its delay and ejection, were the reason behind the extensive ground testing. Now that some confidence has been well established regarding its reliability, this rather long video will reveal the thinking behind each breakthrough as the engine went through several design upgrades before reaching its current form. Now, if you are interested in building your own reloadable rocket engine without any expensive machinery, this could be one of the videos you might want to go through. The materials you need in here can be obtained from any auto vehicle garage and plumbing hardware shop with minor welding processes. From this video, the arrow is pointing to the joint where the nozzle connects to the combustion chamber. Even with a low exhaust thrust, smoke is seen escaping right angle to the nozzle as opposed to being expelled at the back. To address this issue, we have to look back at the past videos of how the combustion chamber gets connected to the nozzle during assembly. This was the initial design, and the exhaust was leaving towards the direction where the arrows are pointing. To get around this problem, I cut out a steel washer and had it attached just as shown here. The circle shows the lower part of the chamber that goes inside the ring seated on the nozzle. The idea was to direct outgoing gases to follow the path the arrows are pointing towards the nozzle. However, this idea was never tested because I googled this space shuttle booster, and as I was staring at its back, I got hit by a revolutionary idea: a hollow bolt and a knot. I immediately discontinued the untested idea. Separating them, I placed the knot on the neck of the nozzle and its accompanying bolt, which also served as the throat inside one end of the cylinder. This was how the gas leak problem was eventually overcome. And now assembling and disassembling is a matter of screwing and unscrewing, as shown in this live demonstration. Now here is a side-by-side comparison of the rear view of the shuttle booster with that of OKB-1. The similarities can be seen from the inside where the idea of the bolt or knot came from. Since both ends of the cylinder were fabricated alike, the gas leak issue is now shifted towards the forward closure, and the arrows are showing where the gases were escaping. This problem solution came from the nipple I picked from the scrapyard, but I had minor problems with it. It was way too heavy and I needed a specific part of it. So I removed the top, which I didn't need, and had it grinded. Furthermore, the accompanying coupling was also repurposed by the cut and grind process shown here. Integrating them goes like this. The hollow ring attaches just below the forward closure, and its coupling on top of the combustion chamber. Assembling and disassembling the forward closure is also just a matter of screwing and unscrewing as demonstrated here. This is how I transitioned from this design to this one, which eventually solved all the gas leak problems. However, this design did not reveal the unforeseen challenges which took me a while to figure out. Now, this terrible performing ground test has to do with the propellant formation. It wasn't properly prepared, even with the casting method wasn't accurate. Then I visited this website, Glenn Research. From this diagram, I came up with this wooden rod design. Here is what was done. I filled the cardboard tubing with the propellant, then insert the rod through it to set this flame front. This gave me the end burning propellant. You notice that the red circle at the forward end showing how the propellant was soaked in the cardboard. This was a problem I noticed with sugar. It solidifies from outside, so loading the propellant as such was a bad idea for me. So I discontinued and went with the cold burning configuration. I noticed that in cold burning configuration, motor instantly pressurizes as the propellant gets ignited, and this is a good thing because the vehicle will very quickly leave the path. Now after the nozzle, the forward closure, and the propellant grain were addressed, for the first time the combustion chamber tube blew up. Let me remind you that that cylinder was a 0.1 mm thick stainless steel plate wrapped to form this combustion chamber. First we have to know why did it blow up. This was how the coupling was attached right on top of the cylinder. Now this created an issue as the propellant grains have been loaded. The red dotted lines represented the thread inside inside of the coupling. Here you see the grain has been obstructed, so I had to reduce its diameter, but that idea created another set of problems. After the grain got reduced so as to pass through, a narrow gap gets created inside the entire length of the combustion chamber as indicated by the blue lines. An additional gap between where the forward closure ends and the last grain when loaded. Well, you can say how about you increase the thermal liner for the inside and make the upper grain taller to close the gap. However, none of this came to save the day. Now, to fix this problem, a much wider coupling is needed, which requires the whole cylinder to be inserted. As you can see, the grain now passes through easily, but you notice there is still a gap issue shown by the shaded area. Here is how I replaced this coupling with this one. From the forward closer looking like this to this one, and this is how the inside looks like. By the way, did I tell you that I now got a better cylinder? Yeah, I do. It is a stainless steel 300 series. Here is another side-by-side comparison of the two and their thickness. Now, with the installation of a new stainless steel pipe, ground testing began getting interesting and scary. Often the motor disappearing from sight, hitting solid structures around. Subsequently, a new location got chosen. Here the forward closer got detached from the threaded ring. It was welded on. Express mail back to sender. Now, while I was upgrading and rebuilding the engine, I thought of determining the amount of force being delivered. With 1.5 kilogram propellant mass loaded, I installed a mechanical scale of 130 kilograms maximum scale reading beneath it as shown in this setup. The scale deformed as the engine fires, indicating well over 1400 newtons was acting on it. However, the motor again separated from the forward closer as observed here. Now this animation shows how that happened. Due to the weight reduction process, I shortened the hollow threaded rings attached beneath the forward closer. This resulted in the number of threads going into the combustion chamber to be reduced. So as the pressure inside the cylinder exceeds the grip provided by the threads, the combustion chamber separated and flew off. Now this was the actual length of the threaded ring, so I had to get a fresh one, but this time around I cut off the full length and had it attached as shown here. With a 510 gram propellant mass loaded, the motor turned upside down with its attachment. To avoid this tipping over, I began the introduction of a sand-filled PVC pipe across the test stand. This, however, hardly stops the effect until I got the idea of placing sandbags to increase the weight behind. Now, this was the forward closer with the hollow threaded ring attached to it like this. Looking at its interior shows where the delay grain and the ejection charge gets loaded. This is how the delay grain is loaded from the narrow passage to the large block broad end. This last part shows the surface area to be exposed to the burning propellant in the combustion chamber. Demonstrate how it works. As the propellant burns, so are the delay grain under motor pressure, but with much slower regression due to its composition until when it reaches the ejection charge. Now this is the way the engine is mounted and screwed on the test stand. As demonstrated in the animation a while back, the PVC pipe you're watching is already filled with sand and pushed through the rear end of the test stand, and the whole setup is now buried. As usual, another test, the motor went inside the lake. Here again shows a part of the forward closer getting detached. The problem being it was only welded on the outside, and inside it has a huge gap which calls for another attention. For the motor to be proven well made after previously failed fabrication, I now switch on to the use of a vertical test stand. This will allow me to load the motor to its maximum 2.5 kilogram propellant mass. And this is how I came with this PVC setup. After rebuilding and closing the inside gap mentioned earlier, you can see that it didn't detach. However, the coupling into which the forward closer screws broke apart. This breakage has to do with the previously mentioned gap between the forward closer and the uppermost grain. The second reason being, I always grind the coupling before welding it on the cylinder. As always, I obtain a new coupling from a plumbing hardware shop and have the forward closer rebuilt again. To prove the fabrication process was done correctly, I have to load the maximum possible mass of the propellant, which turns out to be 2.5 kilograms. The horizontal test stand will not do well in this case, the engine will simply disappear out of sight, possibly into the lake. The best possible way to ground test fire it is by the vertical configuration as in this setup. While the engine was being tested, so was the recovery system. This was done by tying the chute at the nozzle joint of the engine, but away from the main body where it will be subjected to direct heat. This sometimes works, and here is one example of that moment. Now this is the gap created when the coupling got inserted through a pipe, welded only on the outside of the combustion chamber, but it's responsible for those multiple failures. So I decided to close it as shown here with a dotted circle. In addition, I made another jacket around it for extra strength, as shown with the final picture. I noticed one specific part of the motor kept breaking, and it corresponds to the gap that I previously showed you. To address this problem, I made an additional sleeve around that area. This resulted in the broadening of that part of the motor and will not be able to enter the body frame. I went ahead for another ground test fire. To my surprise, that part remained intact. However, the forward closure detached once again. Since this detachment occurred before, I knew the whole forward closure thing and that end of the cylinder had to be redesigned. Instead of the forward closure screwing inside it, it will now go over it as shown here. Here is a visual representation of the forward closure screwing in and over the cylinder. These two objects here are also used by the plumbers to seal water pipes. I don't recommend the one in the yellow-green casing because each tape has a glue on it and it makes the motor very difficult to open after firing. The other one looks like plant fiber. It's my favorite. I never go through heating and hammering the forward closer after firing. With the implementation of the new design for the forward closer, the motor was again tested. That arrow shows where and how the increase in pressure was tearing the forward closer. This was the pipe joint before its transformation to this shape. Overgrinding was responsible for its breakage, and now it has been straightened up under intense force. This is perhaps the best nipple and joint from the many I have destroyed. It is lighter, stronger, and I ensure no part of it was grinded. After opening it, I got it transformed. And that rope was where the recovery system attaches, and this is its interior. Now this was the first time the engine sank inside the ground. The forward closer held good, but for the first time the nozzle blew off, and here was its impact point. This was where it got pushed out. With that problem came the following solution. I first had to hit the cut ends of the cylinder, if not they will break when bending them. Then pour molten brass all around it to seal any possible hole. Furthermore, I put an L-shaped steel plate as shown by the blue shaded area. Then came the final layer as shown here. And that was the last of all major failures in the history of the development of this motor. The pipe joint cylinder separation causes the motor to flow at an unknown height before making another ballistic return. All major areas held up well, except for the part the cylinder and the plumbing pipe joints were welded. I was quick to come up with the idea of first replace, weld, an additional sleeve as indicated by the blue shaded area. This was the beginning of the moment the reusable rocket motor was finally made. However, minor events came up when I began to reduce the size of the hole of my propellant grains. This also increases the pressure inside the combustion chamber, which prompted me to replace the sleeve with much stronger support for that part of the motor. Now if I am to summarize this, teach yourself how to build a homemade reusable solid rocket engine. It will be just two key frames in this lengthy video. First, the use of a hollow screw as your throat and a water pipe joint as your forward closer. I could have stopped from where the gas leak issues were finally resolved. Had I increased the throat size, combustion chamber pressure wouldn't have been much of a big deal. However, I bet for a high power motor, and from all indications it appears that I got one. Reduction in throat size has a huge impact on motor performance because it increases the chamber pressure, which increases the propellant burn rate, thus increase the mass flow rate. Alright friends, in my next video I'll show you how I made my oxidizer from a locally obtained soap making chemical called caustic potash, also known as potassium hydroxide.